Hello, in this video, as I told you, I will give you the something that is related to mathematical induction. And before I give you that, I just want to remind you that the constructions of the real number system is the set of natural number. And Peano postulates or Peano axiom are the axioms that are talking about natural number set. Yeah. And those are true about natural number, right? And this, it's led us to study about induction. Yeah, let me call this just theorem 1.9. Yeah. It talk like this. It say like this. Okay. Let's call it name principle. Yeah, the theorem name is principle of mathematics. Or we can say mathematics, right? Mathematical induction. Yeah. The name of the theorem. And it talks like this. Given you P1, P2 until Pn until infinity are proposition. Yeah, proposition. Yeah. One for each. Yeah, one for each positive integer. Positive integer. Yeah, when we say positive integer, it means that natural number, right? Integer n such that okay, a p1 is true, yeah, and b for each positive integer n pn implies pn plus 1. Then pn is true for all positive integer. Teacher n. Yeah. Maybe you understand. For all words that I have written here. Yeah, let me explain you a little bit. In fact, for this, we call it the principle of mathematical induction or principle of mathematical induction. Yeah, in fact, here we give you P1, P2, P and blah, blah, blah. I mean, until P infinity. Yeah. Proposition for n is a positive integer. And we suppose that P1 is true and Pn true, we get Pn plus 1 true also. For each n is positive integer. Yeah. And then if we give you, we suppose it's true, so we can conclude that Pn is true for all positive integer n. I mean Pn is true for all n that is the positive integer, or Pn is true for all n in the natural number set, right? And here, I mean natural number or positive integer, they are the same. Okay, so to show this theorem, yeah, a little bit short, right? In fact, let capital M equal to the set of small n, which n belong to capital N. Small n here is natural number, right? And Pn is true. Okay. The set capital M here, we set it like this. We let it like this. Let capital M equal to the set of small n, where small n is a natural number and Pn is true. Okay. And from this, in fact, something that is true in the theorem, I mean something that we assume that true, it satisfies M, right? And to show that Pn is true for all positive integer, it means to show that Pn is true for all n that is in the natural number. We just show that capital M here equal to the natural number set. I mean, we just show that M here equal to capital N. Yeah. And how to show this? Again, if you want to show that the theorem is true, you just want to show that capital M equal to capital N. I mean that capital M here equal to the natural number set. Okay? And how to show that? Yeah. And from the definition of capital M, it's clearly that M is a subset of what? Of N. Yeah. Because M is a set of N where N belongs to N, right? M is a set of N where N belongs to N. Okay? So capital M is a subset of what? N. And now you want to show that M equal to N. I mean that you want to show that this theorem is true. So we have to show that N is a subset of M. Yeah. We have to show that N, I mean the natural number set, is subset of M. Okay? How to show this? And we can say that 1 belongs to M. Why? Because see, P1 is true. P1 is true from A. Yeah, A said that P1 is true. So P1 is true, and you can see the definition of M. 1 is belong to M, and P1 is true, and then 1 belongs to M, right? Yeah. And if N belongs to M, then you can get the successor of N is what? Is N plus 1, also belongs to N. Moreover, from B, here, for x positive integer n, Pn implies Pn plus 1. It means that if Pn is true, and then Pn plus 1 is also true, right? So, from B, if Pn is true, then you get Pn plus 1 also true, right? Yeah, it means that if n belong to capital n plus 1 belong to what? Belong to capital N. Yeah. And then if we get from n belong to n and n plus 1 belong to n, then you get n and n plus 1 belong to n. So from this you get what? Yeah. Let me omit this one. And then from this you get n is a subset of n. Yeah. And here you have m is a subset of n. And here n is a subset of m. And then you get m equal to n. Yeah, m equal to the natural number set. And what n and m talk about if they are equal? For m, it talks like this. M is a set of n, which each n belong to natural number, and Pn is true. And now I just change here to be n, because m equal to n. So n, we can say equal to the set of n, which is n belong to n, and Pn is true. I change to do like this. And for n belong to n, Pn is true. It means that Pn true for all n belong to n, right? So you get Pn is true for all n belong to n. Yeah. So Pn is true. It's true for all positive integer n, or Pn is true for all n that is a natural number. Okay? So we have proved our induction, right? Our mathematical or mathematical induction. Okay? Thank you for your watching. Bye.